Okay, Assalamualaikum and good morning. So we will continue what we did last week, and we will restart the lecture that we did on Thursday because of some confusion. So I will clarify today. So we will start from the beginning. Okay, so that this is going to be recorded. So let me start. Oops, I've not shared this. Okay, should be seeing the screen. Can you see it? Okay, good. So let me restart everything. So we are actually going into the topic of lattice discrete translations, and essentially this is actually covered in my set of notes for the first course, but let me just mention that in the first course, by right, one should be doing sort of solving the Schrodinger equation using some periodic potential and with certain assumptions, and the simple case I was like called piecewise rectangular potential, one can actually show that the solutions will actually exhibit energy bands and also energy gaps. So if you want to have a feeling how it's done, then you have to refer to the first set of notes that I've essentially uploaded on Putra Blast, so you can have a look at that. Okay, but in this particular course, we are just looking at it from a different point of view. So essentially, the point of view that we are looking at is the point of view of discrete symmetries and essentially the energy degeneracies. Okay, so the periodic potential is something like in this particular figure, for example. So you can actually see that the situation on the peaks, for example, are separated by a lattice distance of A, or you can essentially take any point on the potential, so you can actually translate that by A, you get to the same what you call potential value at that translated distance. So in other words, it's not just the peak here being translated. You can translate any points on this potential by a distance of A, and essentially you get back what you call the value for that potential at the original point. Okay, so so when do these arise? Essentially, one can think of this as a lattice in one dimension. Okay, one can actually generalize this further if you want, but for simplicity, we just think of a lattice in dimension, and essentially you can think of this where the peaks are, where there are the potential is higher. You can think of sort of core ions, okay, in some material, okay. So you can think of this being repeated at all this lattice site. So an electron, for example, traversing with some energy E will experience the same thing as it goes to a distance of the lattice distance of A. So in other words, each time it passes a distance of A, it goes back to the no, the physical condition goes back to the point where it started off. Okay, so so this is what the sentence is saying over here. So essentially, we would like to implement this symmetry by using a translation operator. Again, translation operator was actually introduced uh, in the same set of notes for this periodic potential, and essentially one could write down what the translation operator is. So it should be something like this: E dx h bar. So this is a unitary operator, and the action of translation operator in terms on the what you call on the observables or the position over here. So this position operator, so I'm leaving out the head at the moment. So it will be translated by the distance of L. So here the parameter is actually L. This is what you call the action of this translation operator in general. So this is the general case. Okay. So you can have L to be any distance. So the action on this observable position here, position operator, will just simply translate that position operator by L. If you want to be more precise, this will be L times the identity operator. Okay. So what about the position eigengets? Then it will be also translated in terms of the distance L. Okay. So that is the behavior of this translation operator, the actions of the translation operator. So what we want to do is essentially to specify this translation length to be the lattice distance. So, and we operate this on the potential energy operator. So the potential energy operator is just simply a function of the position operator in general. But now we enforce that you have this periodicity condition that we mentioned earlier. Okay. So in other words, what we have according to this what we call specified action of the translation operator. So when you translate it using the lattice parameter A, so then your potential goes to V at the point x plus A, but then V at the point of x plus A will be the same as Vx. Okay. So in other words, we say that the potential operator is invariant under this translation. Okay, not the general translation, but the translation under what I call the lattice distance. So that's why the topic is essentially what we call discrete translation, not arbitrary translations. Okay. So if the potential is going to be invariant under these discrete translations, then similarly your Hamiltonian you can actually show that this is also invariant because of your kinetic energy will be just involving a derivative operator. So you go translate it to x dash, and x dash is simply dx plus a. This will just be equal to ddx. Okay. So in other words, kinetic energy operator is also invariant under this translation, and also your potential energy is invariant. So in other words, what we're going to have essentially your translation operator is also, your Hamiltonian operator is also invariant. Okay. So if one look at this is essentially remember that your T is unitary, so your T dagger is actually the inverse. So I should be careful here. T A inverse times T times H times T A must be equals to H. Okay. So I can just multiply on the left hand side by T, and then I will simply TH equals to HT, okay? Or if you bring your TH on the other side, then you get essentially your commutator between H and TA to be equal to 0, okay? So one of the things that we already learned in the first course is that whenever you have two observables to be commuting, then we can say that these two observables can have simultaneous eigencats, or they can be simultaneously diagonalizable, okay? So then one should be expecting that your Hamiltonian eigencats, okay, will also be your it's not equal, but no, it's going to be also translation eigencats, okay? Discrete one. Okay, I think that should settle that. So okay, essentially, normally one can label these eigencats by their eigenvalues. Well, for the Hamiltonian, it's easy, that's the energy eigenvalues, but for the translation operator, now your translation operator is a unitary operator. So in other words, it's not Hermitian, okay? And then what's going to happen is it's not going to be real. The eigenvalue is not going to be real. It's going to be a complex number, and because of the unitarity of the operator, then it will be a complex number of modulus 1. One could actually prove this if you want to. Let's just proceed with this. Now, the idea is now what would be the nature of the eigencats of the translation operator? So this is the thing that we want to actually do. So, and for this particular case, what one would need some handle of making the problems simpler. So one of the things that we can actually assume is that you can have your periodic potential given by what you call, if you think of the earlier case, essentially you can think of a finite barrier. Let's suppose the energy level is over here, the energy level of the, say, electron, so it's sort of still below the maximum of the of this potential eigenvalue, sorry, potential height, okay? So then what's going to happen is that, okay, we'll move freely inside, well, not quite freely, because we have a gradient here. So you will move inside this particular sort of well region, okay, and sort of bouncing back and forth, but occasionally there will be a tunneling probability here, okay? So we'll just pass through and so on and so forth. So essentially this part, we can call it as the barrier part of the potential. Now what we want to do is to idealize this a little bit more by thinking of this barrier potential is actually going to go to infinity. So in other words, this goes up and this goes up, okay? So in other words, what we're going to have is essentially your periodic potential will look like this. Then given that be infinite, okay, so this will go to infinite here. So there is a zero probability of the particle going to tunnel through this barrier, okay? So what happens in this particular case, physically what you have essentially, given if you think of single quantum particle, so it will get settled in one of this potential well, okay? So in that particular case, it's easier for to actually denote a particular state by saying that, okay, the particle is going to be having probability 1 in a particular lattice site. Okay, so we can start thinking of labeling the states of the particle according to the lattice position. Okay, so in this case, what we're going to do, if the particle is actually localized at the end lattice site, then we denote it by the ket n. And if you translate this by the translation operator, so it will go from one lattice site over here to another lattice site. Okay, so in this particular case, your action of TA on the ket n will goes to ket n plus 1, the next lattice position. Now, remember that earlier we mentioned the fact that your energy eigenstate, since it commutes with the translation operator, then one should be able to form simultaneous eigenkets for for the energy as well as the translation. Okay, but you can actually see over here that your localized state, your ket n, for example, is not eigenket of the translation operator. Okay, so we have to fix this in some way to be able to see how we get the eigenkets of the translation operator. But in any case, whatever the state over here is going to be, there will be some particular energy eigenvalue. Okay, so let's consider this localized state, okay, to be in some energy eigenstate labeled by this eigenvalue E naught. Okay. In the book, it's supposed to say the ground state. For me, it doesn't really matter because essentially your barrier is actually infinite. So no, it doesn't matter whether it's going to be an excited state or the ground state. Okay? To me, well, at least to me, it doesn't really matter. Okay. Right. So what's going to happen in that particular case? Okay, I have a certain energy eigenstate, localized state, which is not the translation operator eigenstate. Okay, so but then I can also say that, okay, maybe the particles is localized here, maybe the particle can also be localized here. And remember the fact that at each lattice site, the physical conditions are the same. So in other words, if I go to the next lattice site, okay, you will still have the same energy eigenvalue. In fact, you can actually prove this by just using your commutator just now. Okay, because this is 0, so I can just simply apply what we call tau h on n, okay, and that gives you h tau on n. Okay, so and then this one, you can see that this will actually give you E naught, okay, and this will actually give you n plus 1. Okay, so okay, so in other words, what we have in this particular case is the case of your localized states will all have the same energy, or in other words, the energy eigenvalues are going to be degenerate. Okay, in this context of this infinite potential thing. Okay, so because they are all having the same eigenvalue, so what one could the energy eigenvalue. So what one could do is to do a superposition of all the states having the same energy. Okay, So in other words, I can sum over all possible lattice site kind of eigenstate, the localized eigen, no, it's not eigenstate, sorry, the localized states, okay, and then no, you multiply this with some complex number, and then one can actually define this new state theta, okay, and this new state theta is also having the same energy argument. Okay, one can actually simply just add it on the eigenstate, okay, and then this is just a constant, okay, for each of this particular n, of course, and then you can just bring your h onto the get n, and then you get that. Okay. So what is this theta here? Theta is going to be any real number between the value of minus pi to pi by virtue of the exponential, the complex exponential values. Okay. So what is more important in this particular case? So your theta is already an energy eigenvalue, okay? But more importantly, you can also show that it's also the eigenvalue for your translation operator, okay? So one can actually just bring your translation operator onto this cat n, and it turns into cat n plus 1, and then you can relabel your summation, what I call label n, okay, by n minus 1, and then you essentially get this thing, okay. This is just relabeling, sorry, from n to n minus 1. So your n plus 1 will become n minus 1 plus 1, which is n. So you get that. Okay. And what is this? Well, this can be written as e minus I theta sum e I n minus theta 1. Sorry, already put that into as the common term outside. So that means I'll be left with e I n theta n, and that's essentially your theta here. So in other words, when you operate your translation operator onto theta, I will get some eigenvalue here times theta. Okay. So that, okay, that settles it. So I have now constructed a simultaneous eigenvalue of the energy with the translation operator. Now we want to depart from the idealized case of this infinite potential. Okay, so what we're going to do is now let's consider somehow that you have now, instead of the infinite barrier parts of the potential, we consider a finite case, okay, and we consider in a way such that this is the confusing part from last week. We consider in such a way that the approximation that you need to do is that you still have the idealized state of this localized states, okay, like in the case of your infinite potential, but now you allow it to seep through, tunnel a little bit through the potential barrier potential area into the other sites. Okay, so let's consider that, and then what we're going to do, we think of how the Hamiltonian your Hamiltonian to be some. Actually, I should be doing some kind of perturbation theory, but no, it's not necessary. But I can think of this, the initial case is the one with the infinite potential. Okay, but I'm just actually that's not quite right as well. In other words, what we would just want is to reuse these localized states that we had earlier. This particular localized state, and use that as a basis in some sense. Okay, and then you have a Hamiltonian that gives you some kind of possibility of tunneling through between lattice. Okay, so in other words, this will involve some kind of interaction between sides. Okay, it might be even no. This in a way is like a perturbation thing, but no, it could be something much more complicated than this. Okay, I'm just trying to display the possibility. Okay, so one thinks of, okay, how can I actually write this Hamiltonian operator? So you start putting around the matrix elements. So one in general, one should have, say, matrix element H, which is, you can relabel this H and M, for example. Okay. So one of the things that we know, for example, if this is if you think your N and M, this is the thing that got me confused last time. Your N and M here are still thought as the idealized localized states. Okay, but your Hamiltonian might be able to might consider possibility of things being tunneling through. Okay, so I'll try to explain this a little bit afterwards. Okay, so in other words, what's going to happen in this particular case is that you have the diagonal elements, and the diagonal elements reproduce the energy levels, the energy eigenvalues that we had before for the localized states. Okay, and this will work for all possible lattice sites. Okay, so you can go to n plus 1, for example, and you still have the same energy eigenvalue. Okay, so so that gives you a kind of the diagonal element. But now one starts to consider, okay, let us consider the possibility of having a general matrix element in this way, but we would like to simplify this. So how do we simplify this? The only possible non-zero matrix elements that you can actually have is that when N and M are related by just one lattice site, okay, a neighboring lattice site. So in other words, we consider the case of non-zero matrix elements in this way. Whenever it is, of course, when it is equal, okay, you get back to the diagonal case. But if it's just one lattice site on the right or on the left, then you still get a non-zero matrix element. Okay, so this is the confusion part. Last time is, no, I was thinking of this is already what you call the state, which is different from the localized eigenstate. Okay, so now we still use this as your localized eigenstate are still considered as your basis of your Hilbert space. Okay, so with this kind of condition, this is what we call in solid condensed matter or solid state physics as the binding approximation. Okay, and let's start to give us a value to this particular neighboring site kind of matrix element. Let's consider that this is actually equals to minus delta. Okay, and this is where I got confused last time. Okay, remember that this localized states okay, are still the idealized one, and for the idealized one, you know there's no overlap. This will have to be orthogonal. Okay? So in other words, the fact that you can have this off-diagonal thing is due to the Hamiltonian. So the Hamiltonian will contain terms that allows this transition between adjacent lattice sites. Okay, and one can actually show using this particular condition. Okay, or this condition. Okay, then one can actually show that your Hamiltonian acting on n is not just simply E naught times n, but it has all these diagonal off-diagonal elements here, okay, given by this minus delta. Now, how do we actually show this? You just simply try, you can check what happens when h, when your elements are that, and when your elements are n plus 1 h n. Okay, so it should reproduce you this one, and it should reproduce you this one. Okay, so I think that settles our confusion earlier. So once you have this, so what does that mean? So essentially when your Hamiltonian acts on n, if it's an eigenstate of the Hamiltonian, then it will just give you a value times n. But it's not. Okay, you have these extra terms coming in. Your ket n is no longer an energy eigenstate. So, okay, one could ask what would be now the simultaneous eigenket of your translation operator and your Hamiltonian. Well, let's consider the one that we already had before. Your translation operator will have this as an eigenket. Okay, so this one needs to check if this is also an energy eigenstate. Okay, because we already know that this is essentially a translation operator eigenstate. So one just need to check whether one can have this thing also as an energy eigenstate. And in fact, what you can have, if you just apply that to theta, so this is h theta now. Okay, so that means I will have your, remember the terms that we had earlier, so this will become, remember this is n e I n theta hn now, and we know your hn from the previous action before is given by that. Okay, so now we can do this again. One can start to relabel things so that your ket is labeled by n, and then this will change to something else. So this will be, in this case, e n minus 1 theta, okay, and then this will be e n plus 1 theta. So what you have is essentially we have that. So I can bring my, in this case, I will bring my e minus I theta and e plus e power I theta outside, and you'll be able to form 2 cos theta from there. Okay, so you combine all these terms coming in with this common eigenket n. And then we get that, and this is essentially theta. Okay, so in other words, what do we have? H theta acting on this superposition thing gives you this eigenvalue, okay, times theta itself. So in other words, theta is actually an eigenstate of your Hamiltonian. Okay, the only difference that we had before is now there is a slightly different contribution coming here. Sorry, just looking at the cat. So where was I? Okay, so there is an extra contribution here, and it actually involves your delta that we mentioned earlier that gives you this transition thing. Okay, this one, and it is labeled in this particular case by that theta that you bring out from the sum, giving you the cos theta. So in other words, we have this eigenstate, okay, with an eigenvalue that depends on the continuous parameter theta. Okay, so in fact, if we think what kind of eigenvalues this is going to be, so your theta ranges from minus pi to pi, so you get the case of E naught when pi is actually pi over 2, sorry, when theta is pi over minus plus or minus pi over 2, then essentially you get, is that right? Pi over 2 is 0, sorry. Plus or minus pi, sorry. Getting confused. So when theta is plus or minus pi, then you get essentially these eigenvalues. And then you can have any other eigenvalues corresponding to the other angles of theta. So there would be a band. Okay. I think I have the diagram below. So this is E naught minus 2 delta and E naught plus 2 delta, and then all possible eigenvalues in between. So that gives you the band. Okay. So again, with just simply having the tight binding approximation, we do not know the details of your potential in this particular case. We are just assuming, okay, you can have this localized states, okay, which is coming from the idealized potential earlier, and then you just introduce terms inside your Hamiltonian in such a way that you can have transition between adjacent sites. That's all the assumption there is. Okay, so for that kind of approximation, we use feature of the energy band. Okay, the other general feature that one can actually get from this tight binding approximation is the following. So you consider now your wave function. Your wave function, remember, are just position representation of your state. So for example, the theta state that we had earlier, so this will give you some kind of function here, okay? And then you consider what happens with the translated case, okay? Then remember I mentioned about the translated case, for example, psi x t of a, what's going to happen, this will be translated sort of backwards, but the picture that you're supposed to have, this argument with the x going backwards, it's actually giving a picture of wave propagating to the front. Okay, so okay, so we have that, and then the next thing that we are able to see is that this TA acting on theta, we already know what that is. That's essentially giving you that. Okay. So in other words, combining these two equations, then we actually have the following. And then what we're going to do, we're going to do some kind of sort of parametrizing the equation a little bit different by writing it as theta equals to Ka. Okay. Remember, your theta is a function that's supposed to be what you call having all this lattice side be equivalent in a way. So it has this property that has this parameter, lattice parameter is going to be somehow related to your theta. So we have that over here, and then this is just another parameter that tells us how the wave is going to move forward, for example. Okay, so you have that. Okay, and you plug into all the conditions that we had before. The other thing that we need to have is that we need to consider the condition. Remember that this will be a function of x dash. Okay, you already have this part, okay, which is a function of x dash as well. So this is like your propagating part. You remember in the first course we talked about wave packet. So this is like your why is it not appearing, modulation thing, and then you have the carrier wave. So this is the propagating carrier wave. Okay, and modulation, it must follow the periodicity of your what you call lattice or your potential. So in other words, what we need is that this modulation factor will be a periodic function with the period. Okay. So you substitute all of this and see what we get. Okay. Well, essentially you get a tautology. Okay. So essentially on this part, for example, okay, you actually substitute into this. Okay, this part essentially give you this, and this part essentially give you this with this parameterization thing. And if you check this exponential, you can combine them together. And then this one is periodic under translation of A, so this one will be just UKX. So in other words, the left-hand side equals to the right-hand side. So in other words, what do we have? We have a solution here given by this for this particular equation. Okay, but what does this solution tells you? Well, this is essentially the thing that we already seen before. This is called the Bloch's theorem. Okay. So in this particular case, the Bloch's theorem is utilizing this theta state, okay, with this parameterization thing. And this theta state is coming from the case of your tight binding approximation. Okay. So now what do we have? So your solution here is now being parameterized by k, and k is the thing that I mentioned earlier. It's supposed to tell you about how the things propagates. Okay, so your k essentially is what we call the wave vector. Okay, and because of that, since you have this condition that we had earlier on the eigenvalues, then you'll find that your eigenvalues is also going to be parameterized by this particular value of k through this cos theta. Okay. How is this possible? Because your wave vector these values which comes from these values of theta. Okay. So again, this is just a picture that we have seen earlier. This gives you the band structure thing. Okay, what else? Okay, the other thing is this part that's been drawn here is sometimes called, well, it's called the Brillouin zone. Brillouin zone, sorry. So all one needs to consider usually in calculations to, to restrict ourselves to this brilliant zone. Okay, so that settles for the lattice discrete symmetry. So the next thing that we want to look at is the idea of time reversal operators, and the time reversal operators involve anti-unitary and antilinear operators. Before we do that, let us take a short break. Is that okay?
Oh, doctor, five wasn't uploaded on Tutor Plus.
Lecture note 5. Which one is that?
With Wigner-Eckhart theorem.
Ah, okay. Okay, I'll do this after this. Okay, everyone's back. All right, let's continue. So what essentially what we're trying to do in this sort of lecture is to be able to take into account all possible discrete symmetries that we can actually find. So far we have seen two. One is the parity case, and the other one is your discrete lattice translations. There is another one. Actually, there is another two, really, but the one that we are going to do at this particular stage is a very nice one, or intricate in some sense, is because the symmetry that you get from here is probably hidden in a way. So this discrete symmetry is coming from where? It's coming from equations of motion. Okay, so take the case of the classical case. You have your usual F equals ma thing, okay, and if you try to solve, let's say, get the solutions to this, you'll get some solution of r as a function of t, satisfying this equation motion. But now this particular equation doesn't really care well, I mean, it does care, okay, but for the condition that we have over here, this is telling you what? This is telling you that you have a conservative system. So conservative system or conservative force for this matter, okay, this is actually the force. And for conservative force, it doesn't really matter. So here we are not assuming the case of things with friction, so neglecting the case of non-conservative forces. Okay. So if we restrict to this limitation, okay, what happens when you try to solve this particular equation is that if you get the solution, I can just simply flip your t goes to minus t, and then the solution that you get from making the function evaluated at minus t will also be a solution to the equation. Okay, so in other words, there is this possibility of flipping your t to minus t and still getting you a new solution. In other words, a new possible physical condition. The only thing over here, one should be careful on how you interpret this. We are not going back in time. We are just reversing the time arrows. Okay. So in other words, if you have a time arrow moving forward, then you just make the time arrow looking backwards. And in the particular system that we are looking at, it doesn't really matter the solutions. You still get a solution of that equation of motion. Okay, So that is pretty straightforward from the case of F equals ma, but you actually have this, most, if not all, most of the equation of motion in physics are essentially time reversal invariant. Okay, there are only a few exceptions, and of course, if you include all the non-conservative force, then okay, then there would be the majority of the solutions will be not time reversal invariant. Okay, these are only limited to the case of the conservative force. Okay, so so in other words, we have to include this symmetry somehow inside your inside your quantum mechanics, because it's there in classical mechanics. Okay, and what else? Okay, the other thing that one should also remember, it is like the case of your space reflection thing, your parity thing. Okay, you change from r goes to minus r, and then you do again, and you get back to the original case. The same thing happens over here for your time reversal thing. So getting back to the original case after twice operation of your say, parity here and time reversal here, this is what we call, well, actually in maths, they call it as involution. You do the operation twice, you get back to the original case. Okay. Now, for the case of electrodynamics, it's slightly subtle a little bit because of the appearance of certain fields that doesn't quite actually, they are not in this so-called mirror symmetry in some sense. Okay, but let me just explain what it is. So, so your Maxwell equation are this electric field equation involving electric fields and magnetic fields, and this is your current, and this is your charge density. You can still reverse the time in these equations, or the other equation I should mention is again your F equals ma kind of thing. This one, this is the Lorentz force equation. Flip the time, but you need an extra thing to do. Okay, flipping time, you'll be able to get this kind of transformation. Your current going forward in time is also under the time reversal transformation will go to current going backward in time, and then motion forward in time will be replaced by motion going backward in time. Okay, and then your E will remain the same, your charge will remain the same. The one that sort of gives you a slight difference is the fact that your magnetic field should, along with the time reversal, should change to a negative B. Okay, this is essentially because your B is really a pseudo vector. Okay, so if one remembers, you have also things like your magnetic field is in this particular case, if you have, I think this is, I'm not quite sure what rule is this. This is a right hand rule, I think, right? So if your electrons moving in this direction, you get your magnetic field going here. But if you reverse, what's going to happen? It's going to go the other way. Okay, so that's the only reason. So in other words, if you want to impose time reversal invariant in the theory of electrodynamics, then one impose it together with this transformation. Then you actually get a theory which is time reversal invariant. Okay, so that is the classical case. Now the question is, what happens? What is this? Oh, it's the file just now. So what happens in the case of the quantum mechanics? Well, quantum mechanics, you have essentially your equation of motion are given by Schrodinger equation. So let's write it down. So you have your H bar decided. So this is the time dependent one. Okay. So if you look at this, so your psi will be a function of R and T. So if one tries to change T goes to minus T, then one should get this function. But this function will not give you a solution of this equation. Okay, you can check it for yourself, but the best thing to do is to think of your, let's consider your what you call your stationary state solutions. Okay, so it's the solutions with solutions of which is of the eigenstate, energy eigenstate, sorry. Okay, so the energy eigenstate are stationary states, and your energy eigenstates will evolve according to time using this particular phase vector. Okay, so this, if you look, what happens if you make t goes to minus t, then this will be a plus, and then essentially what you get instead of En to be your eigenvalue for energy, you'll get instead of that minus En. Now you say, so what's wrong with that? Well, what happens is that En will go from, in the ordinary case, En will go from your ground state upwards. Okay, so it's bounded below and not bounded above. So if you have this and flip the other way, then essentially what you have is your energy states will not be bounded below, and that causes a problem. Okay, so in other words, we have to do something else, just like the case of your magnetic field just now, electromagnetic field. Then we do some extra thing to make sure that everything goes back to normal, in a sense, if you do the time reversal manner. And what's the thing that we need to do is to complex conjugate it. Okay, remember when we did t goes to minus t, this actually gives you a plus. Okay, plus IET on h bar. But if you complex conjugate it again, then you get back to the exponential minus IET on h bar, and this will give you back the condition that we had for this case. Okay. So in other words, in quantum mechanics, time reversal will need to be coupled together with the conjugation process in for this wave function, for example. Okay. So in other words, we need to be able to consider this, but for the time reverse state, it must be considered the case with the conjugate. So how can you let's call this let's call this psi star. So how do you actually implement such a transformation going from psi to this psi star with the time reversal part together? Okay. So this is the thing that we want to do. So let us recall what kind of transformations we have in quantum mechanics. Okay. In the past, we have already mentioned that your unitary operators actually allow you to actually change basis of your Hilbert space. Okay, and that will actually give you this possibility. So for example, if I multiply a unitary operator to this particular state alpha, I will get, say, another equivalent state of alpha tilde here, and the same thing for beta here, I get beta tilde. And then what happens if I do a inner product between the two, I get beta tilde alpha tilde here, and this will give the same values as beta alpha. Okay, because why? This gives you the identity. Okay, so that is well and good and understood. Okay, essentially all your symmetries inside your quantum mechanics are mostly given by unitary operators. Okay, but how can we implement the time reversal case? Well, in this particular case, one needs to this condition is actually a strong condition. Okay, because it's a condition on the inner product. Okay. What you need is actually a weaker condition, because in quantum mechanics, most of the time the thing that you need is essentially you take the magnitude, because the inner product itself, okay, the inner product actually gives you some values inside C. Okay, so in other words, in terms of relationship with physical quantities, this doesn't do it. So what happens usually is you multiply by the conjugate, right? And then when you multiply by the conjugate, then you get your magnitude square of the complex number. Then you get essentially that would be a real number. Okay. So the point here is now it's not the inner product itself that you should ensure to be conserved, but it's just the magnitude of that. Okay. So in other words, this is a weaker condition. This in fact is a condition on your probability amplitude rather than your inner product. And probability amplitude is well, actually is I should say, should be careful with the word amplitude here, but essentially your probability amplitude square equals to the probability. Okay, so magnitude is what we want. Okay, so how this would actually help? Well, the point is, in this particular case, we must have the time reverse state. So remember, your alpha tilde is the one being transformed, and your beta tilde is the one being transformed. So consider that your alpha tilde and beta tilde are the time transform one, the time reversal transform one. Okay, all you need is to make sure that, okay, because I just want this, I don't need to make them equal in the inner product sense. I just need, I can have, for example, a complex number Z. Okay, if I impose it to be, if I impose Z under the magnitude, you know that this is possible, right? So in other words, I can have instead of having just the Z condition thing, okay, I would have, so in this case, you will have both equals to, sorry, one above, both of these will equals to Z, okay, because you have this unitarity of the operators, okay. But I don't really need that. Okay, I just need this condition. So in other words, one possibility is just to have Z. Okay, the other possibility is to have Z star, the conjugate. So the other possibility is to have, instead of equals to beta alpha previously, okay, previously is the case of this being equal, I can just use the fact that I can use the conjugate. Or in other words, if this is beta tilde alpha tilde, then I just need to make sure that this is equals to alpha beta. Okay. So let's do that. So we weaken a little bit the condition that we had before. So, and one actually do this by this, assume this, what you call this, condition for the conjugate case for this time reversal operator. Remember, this is in fact implied from the thing that we have discussed before, that we need to do the conjugation, right? So essentially this is what we did over here. The weakening of the condition is to allow this conjugation to come in. Okay, so let's do this. We consider this operator now to be the kind that sort of allows you to do time reversal transformations. So this is like this symbol is actually if you do latex, this is right. Okay, so that's what it is. It's actually T in a different form. Okay, so let's consider that to be the one representing the time reversal transformation. So in other words, when it adds on alpha, it gives you alpha tilde. When it adds on beta, it gives you a beta tilde. But the condition that we need is that this beta tilde alpha tilde, the inner product, it doesn't have to be equals to beta alpha, but it can be equals to alpha beta. Okay, so that's one condition. Okay, I call this condition star. And another condition is that one requires the action of this operator that is supposed to do this time reversal thing act on this superposition. So this C and D is a complex number. Okay, C D here in C. So what's going to happen if we do that? The action on this is your complex number gets conjugated, and then the other thing is just like your linear case. Remember a linear operator. This is a linear operator, so linear operator is what? So I have a O here, say X on never mind. I just want to remind you what linear operator is. So let's say O acting on say C1 alpha plus C2 beta. So this is a linear superposition. C1, C2 is complex number. Then a linear operator is simply just the one that distributes the action of the operator O. Okay. So here it's almost the same kind of thing, but instead of being a linear, this is the condition of what we call the antilinear operator. So this condition double star is actually an antilinear operator. Okay. And if you combine this property of antilinear operator together with this particular condition, then we get what is called antiunitary operator. So the antiunitary operator has both star and double star. Okay. Now we'll try to do this. So what we want is now you have an antiunitary operator to represent your time reversal operations. So And we know that that will also involve this antilinearity of the no, character of the operator. So one can actually do this kind of decomposition of the operator. So if you have an anti-unitary operator, then it can be written in terms of a product of two operators. One is U, where U is a unitary operator, and the other one is K, which is an antilinear operator. Okay. So if we do that, you can see easily that actually works. Okay. So let's just do the one on the superposition thing. So T is equals to UK. So K will transform the coefficient C and D here to C star and D star over here. Yeah. So that is just so in other words, K going acting on this. So K acting on C alpha is ready equals to C star K alpha. So this one is left undetermined. Okay. So same thing over here. Okay. So you get K alpha here, and then still you have your U, and U it acts like a linear operator. So then you just simply distribute this way. Okay, it doesn't change anymore the conjugated constants here. So you come back to the point of combining U and K here to give you the operator T here and operator T here. Okay. So that gives you the second condition. Okay, double star. Okay. This is just your antilinear property. Okay, so in other words, the antilinear property is just coming from that antilinear operator K here. Okay, but we still need to have the first property, which is coming from equation star, which is this one. Okay, so we need to show that as well. So let's do the following. This one is slightly different from the one in the book, but no, sometimes the book doing a little bit more complicated way of doing things. So I'm just going to simplify this. So I'm going to show, just assume a basis. So the basis will work for both alpha and beta. So this is just your coefficient here, the expansion coefficient for alpha, the expansion coefficient for beta, multiplied by the basis. Okay. So now what we need to do is to transform this now, okay, into the time reverse one, which is now given by beta tilde and alpha tilde. So what does this correspond to? This corresponds to your time reversal, the one that implements the time reversal transformation, okay, on the cat, and then for the corresponding one, it should be an adjoint of that, okay, that will act on your beta. Okay. Over in the book, they start to talk about considering only actions on the cat rather than, and then they don't care. Well, not to say they don't care. They use another argument to say that okay, you do not want to consider action on your bra. For me, it's just enough to do the dual. So you always, for any operator, say X on, say alpha here, there will be a dual, okay, for whatever operator here. It doesn't have to be Hermitian, it doesn't have to be unitary. Whatever operator, there will be a dual X dagger acting on the bra. Okay. So we use this duality condition. So in this particular case, we have that duality for your beta alpha, okay, and then your beta, okay, your beta is, no, you need to should I say, to decompose this according to the basis. So I have that. And then your alpha, also I have, I think I'm missing an EI. Okay, so I have that. So this is your expansion coefficient here times EI. Here it's being conjugated because it's a bra vector. So this is the expansion coefficient, and then this is the bra vector. Okay, so this is the basis. This is the basis for bra. Okay, and then for your so-called time reverse operator here is given in terms of UK, where U is unitary, K is the antilinear part, and then the same thing happens for your dagger. And remember, the dagger for general operators, it doesn't have to be any condition on the operators. X, Y dagger is always Y dagger, X dagger, whatever the operator is. Okay, so I'm just using that. So I have K dagger, U dagger. Okay, and then over here you'll see that I have U dagger U. I don't know what happens to the curly bracket here, but it's supposed to be there, and this B equals to 1, this U dagger U, and I'm left only with this operator K acting on this cat and operator K dagger acting on this bra. Okay. So the complex number here is this one, and the complex number here is this one. So this one gets flipped by a conjugate. So this turns into EI alpha star. Oh, I've forgotten again. Okay, in this particular case, that's one thing I would need to assume. Perhaps this is why the book doesn't want to do this. Your basis state will remain. Okay. I think it's quite reasonable to think of this. Let's consider your EI. I think the book also did that at some other stage. Your EI is just like your column matrix. Okay, so the 0, 0, and then there's a 1 somewhere in the I position. And there's no problem of this antilinear operator acting on this thing. There's no complex number here. Okay, so essentially that's the assumption. Okay, so given this, okay, I would now only have this thing been turned to a complex conjugate, and this thing been turned to in terms of a complex conjugate, and I still have your bra EJ here and your cat EI over here. And your complex conjugate I can rewrite in this particular way. Okay, it's not going down. Okay, so I can just rewrite that thing by the changing the position of your bra and cat. Okay, and then I have this one operating on EI here, so EJEI will give you a Kronecker delta. So I will be able to change the index here to be the same. So I have that. Okay, and that essentially just the identity operator, and I'm left with alpha beta. And this is precisely the condition of star. Is it? Is the condition? Yeah, here. Okay, so we have actually proved that with that decomposition that is good enough. Okay. The only thing that one has to be careful here, I don't assume anything about K dagger. So your K dagger is just the dual of K. So if I know how k acts on cats, then I should know how k dagger acts on grass. Okay, so it doesn't actually it's not equals to the inverse, it's not unitary. Okay, so that sort of leaves us to where I finish my notes. The next thing is, no, I don't have, no, I'm still typing the notes, so I will have to actually go to the book. Any questions so far? Let me just from at this particular point. This notes has been uploaded on your Putra Blast, so you can have a look. So I'm still writing out the lecture 9. So what I'll do instead is just to use the book of Sakurai. So if there are no things, so let us just continue then. So this is my notes. Let's go to Sakurai. So now let's properly do this for the case of the time reversal transformation. So we know what it's supposed to look like. It could be a combination or a product of a unitary operator multiplied by an antilinear operator. Okay. So let's now make the thing a little bit more specific. Okay. Just now it's essentially the discussion that we had earlier is targeted to a more anti-unitary operator. Okay. So we will now actually implement the time reversal itself by adopting a different symbol here. I mean, initially I thought I just use the same symbol, but now I will just follow Sakurai. So we adopt this symbol to represent the transformation of t goes to minus t. Okay, so in other words, theta alpha here. So this is capital theta. Nobody seen capital theta before. Okay. So this is capital theta, which is representing the time reversal operator. Acting on this state gives the well, in our case before, this would be your alpha tilde. Okay. So there are some things that one actually expect to happen, but we will try to do this properly. So if, for example, your alpha here is your momentum eigenstate, say P dash, then you really would like to expect that this will turn to a minus P dash. Okay, and so on and so forth for the other things. Your position, for example, will not involve time, so that it will get unaffected by your time reversal transformation. Anything, any quantity that involves time will get time reversed. The one which is not explicitly depending on time, then it doesn't get time reversed. I mean, it's identical to the original state. So we want to make this a bit more precise. Right. Let me think. What is this? Okay. Okay. This is trying to see how the time reversal operator interacts with the time evolution operator. So as expected like before, now of course the time part will get reversed, But one should also remember the antilinear part, which somehow it doesn't actually say here, or maybe later. Okay. So here is the time evolution operator acting on your state alpha here, and then one could consider the case of your time reverse state, okay, given by this, and then time evolve it again, okay. So what's going to happen in this particular case, if you do this sort of product between the two operators, then you can actually show this one. So here is your evolution operator, theta, and then theta evolution operator. Then you expect your part involving time should be giving you a minus delta t. Okay. So if one expand this whole equation out, then I can reduce this to this equation, which says minus IH capital theta equals to capital theta IH. Okay. Now, this is just the argument that your theta cannot be unitary, so I'm not going to go through that. So because you already know that theta has to be anti-unitary, okay, so let's assume that instead. So here is the thing that we're supposed to have. So we cannot have, for example, this equation. This equation will imply what I call contradictory results. But the right equation is to say that we're going to have this I that appears in the previous equation also gets turned into a minus I. Okay. So essentially this is the thing that we have. And because of the antilinear this part, for example, the antilinear part will act on this I to give you a minus I, okay, and that will actually give you in the end theta h equals to h theta. Okay, I'm skipping some steps because I don't make notes for this yet, so bear with me, everyone. So theta will be anti-unitary as mentioned. Now this is going to be, again, it's just a repeat of the things that we did for the general case of an anti-unitary operator. Okay, so now your theta is having this property of being a time reverse operator. Okay, now we would like to see how this would act together with other operators. Initially, I get confused by this equation of 4.4.36. Introduce your what I call this X-Men operator. This looks like a tensor product thing. Okay, so I do not want to use this. So you can get confused with the idea of tensor product, which is actually not. Okay, this is just the point that the author wants to make is that you consider any other what I call linear operator, and then how is the interaction with the time reversal operator. So if you see this symbol here, you can actually replace it by, see, another symbol. Let me just write it down over here. So I have plenty white space here. Beta, so I'm going to write L to be a linear operator. So I will have now beta L alpha, and it claims that under the time reverse state, this would be equals to alpha tilde time reversal operator L dagger time reversal operator the inverse times beta. Okay, so essentially this is the identity, so please don't get confused. I get confused initially when reading this. I say, what is this guy trying to do? Okay, but essentially I can replace this by any other symbol beside that symbol, okay, and think of it just as a linear operator. Okay, a linear operator I already defined earlier just now. Okay, so now what's how to prove this? So essentially the next thing is to prove this identity, and this identity says how the linear operator behaves under the what you call time reverse operation. Okay, so here is essentially a definition to say okay, since I'm going to have where is it okay, since I'm going to have an L dagger, sorry, this is L here, so I'm going to have your L dagger acting on your this particular state. So I would need to know how that actually works. Let me mention the other thing. Okay, I'm not quite sure why is it using here. But okay, remember that your beta tilde is just capital theta times beta. I can just multiply the inverse on the other on both sides of the equation. Then I actually have this. Okay, so your beta here. So in other words, your beta is actually appearing here. Is related to the time reverse transform by this operator, time reversal operator inverse. Okay, so this is just using the inverse of that. Okay, but now over here it appears as a capital appears as a bra vector instead. So this is why it defines over here. So it wants to show what is actually happening on your bra vector. So here we are defining gamma here as the action of L dagger on beta. Okay, so the dual of this, okay, the dual of that is essentially equals to the bra gamma equals to bra beta acted upon by L. Okay, so that is actually this one. Okay, so now one can look at that. Okay, remember that this is actually that now. So I can convert this beta from beta here to beta tilde. Okay, so that's essentially the thing over here. So this, so remember this, now you just need all to replace by that. So this is gamma, okay, gamma, bra gamma equals to bra beta L. So that is just bra gamma there, and alpha here is alpha here is no, we didn't do anything over here. Is that thing, okay? So we just transforming the redefining your L beta here by gamma. Okay, so we have that. But we also know that, okay, the relationship between the time reverse one and the original states are just by a complex conjugate. Okay, so in other words, gamma alpha here is going to be related to your alpha tilde contracted with gamma tilde. Okay. So now let's put all this thing in. Go down. Right, and let's see, in this particular case, what's happening here is to rewrite your gamma tilde here. Okay, gamma tilde here is your gamma is that. Okay, so your gamma tilde will be involving your time reverse operator. Okay, so I have that coming from the definition of gamma tilde. So we'll get that. So remember that this is L dagger. So the next thing here is just to introduce an identity here, and the identity is decomposed by capital theta inverse times capital theta. Okay, and then what's happening here is that I can use theta beta from above, which is equals to beta tilde. Okay, and I'm left with capital theta L dagger theta inverse times beta delta. Okay, so that actually gives you, okay, the identity that you need, which is here, sorry. Okay, your beta L alpha is equals to alpha tilde 1 is the time reverse one times theta here L dagger theta inverse beta tilde. Okay, so I will do this properly in the notes later on, and essentially hopefully this is a less confusing notation than the one given in the book. Okay, so now one can actually apply this to any observable. Okay, the operators that we normally assume in quantum mechanics are all linear operators. So we are doing linear quantum mechanics if you want. There are things which is no, there are areas called nonlinear quantum mechanics. We are not doing that. So all the operators here are just linear operators. So we have done the general case. Now we can apply it to the specific case, in particular the Hermitian observable. Okay. So in other words, we will have that equals to that. Okay. So the point is now, okay, that is in general, okay, the relationship between the time reverse version and the original version. Okay, remember we always use the fact that we are making correspondent with the case of the classical case through the expectation values. So essentially that's why we need all these grass and cats still into the picture. But now you can actually see the time reverse operator version, okay, is related by this condition. And our next task would be, hopefully, I think I will stop at this particular point. Our next thing will be is to consider specific cases where your operators are going to be either even or odd under time reversal. Just like the case of your P just now, this will be odd, okay, and the time reversal, and your your position operator will be even. Okay, so we'll do this hopefully in the next lecture. By the way, the next lecture is it falls on Thursday, and Joshua, is it true it's a holiday?
I heard that from another class also, Doctor.
Okay, if it's a holiday, then we will not have the Thursday class, but we have to replace the one that we missed last week. Okay, we'll find some time. Okay. But this Thursday, there will be no 3 p.m. class. Okay, because the state, I think it's only the state holiday. Negeri Sembilan is not a holiday. Okay. So, any other questions before that? I leave. So I will download the attendance list. Okay. Okay, so if there are no further questions, thank you very much. So I'll see you next week. Well, I'll see you later in relativity also, yes. But for this particular class will be next week. Oh yeah, just remember it's supposed to be a test, right? Okay, so your test, apparently they have started to do all this rotation for being to be in the faculty. So I'll be in the faculty on a Monday morning. So I'm just afraid I'll arrive slightly later than 8. So I will start the test at 8:30. Okay. I will. Okay. All right. So your test is 8:30. Okay, everyone.
The coverage up to again.
Pardon?
Up to which lecture is the coverage?
The test one will be until the Whitney card thing, which is also the point where you did your assignment, right? So oh, by the way, your assignment should be due today, right? And then I
More
will.
time, Doctor.
Pardon?
Yeah, can we have a bit more
We have a
time?
bit more time. Just not trying to figure it out.
When do you want it?
Good question.
Okay. The latest will be okay. Let's put it on Friday.
Okay.
Okay.
Okay, doctor.
All
Wait,
right.
doctor,
I think
could I,
Okay.
doctor,
Thank
could I
you.
ask how does a rotation operator act on spherical harmonics?
Oh,
Well,
yeah, number 5.
I think that is with you have to arrange the if I'm not mistaken, I can't remember the question now. If I'm not mistaken, you have to arrange it in terms. It's like the vector operator thing. So you have the components coming from your M.
We're supposed to use the spherical tensor instead of spherical harmonics.
Which question is this? I can't remember now.
Number 4.
If it's just the rotation operator, then you just need to see the components. So the one with the spherical harmonics is the one with the spherical tensor. Okay. Or we can discuss this later. You let me know which question is actually. We can discuss later. Okay. So end this now. So thank you everyone.